Hello everyone. Today I am going to explain about the latch-up condition in CMOS circuits and how we can avoid that latch-up conditions. We will see now. Okay. So here we have what is latch-up. Latch-up is nothing but establishment of direct connection or the low resistance path between VDD and VSS rails due to the parasitic elements is called as what? Latch-up. Okay, so here I have the latch-up in CMOS circuits. Okay, so where we'll get this one means while doing the fabrication. Okay, so we'll get this latch-up condition, so the formation of the parasitic elements. Okay, so like when I will explain what is that parasitic here. So first we will go with the definition here. What is definition? Latch-up is a condition in which the parasitic components gives rise to the establishment of low resistance conducting path between VDD and VSS. So if I consider VDD and VSS here, so this is nothing but due to the parasitic elements, what happened here? There is a direct low resistance path will be established between the VDD and VSS of the CMOS circuits. Okay, so this is called as latch-up. Okay, so because of this latch-up, we'll get the very distortions in the output of the CMOS circuits. Okay, so here first I will consider here. So what are the latch-up effect in P-well structure? How it will form? So if you consider this one in P-well means P-well process means while fabricating the CMOS, we require a P-well, okay, and a substrate, right? So if I consider here P-well process means we have to consider N substrate. Okay, P-well means we have to consider N substrate. So here it is the N substrate. Okay, so it is N type material, and again we have here we have N plus, okay, and P plus. So P plus means if we consider this one is the N substrate, so this transistor is of P mass, and it is a P-well means it is of N mass. Okay, so in P mass transistor, the source and drain of are of P plus. That is nothing but active P regions. Okay, this one is the source and this one is the drain. Okay, and this one is the substrate contact what we have to use. Okay, so if you observe this one, this is the substrate, right? So this is of N type and this one is of P type. Okay, this is of N type and this one is of P type. So here there will be a formation of a transistor. Okay, so here I will consider that this is nothing but what? P, right? So this is the substrate, so this one is N, and again we have this total is P-well, so here also we have P. So here if you observe this one, this because of this one, this P plus, okay, so there will be a formation of P region or connection here, and at the same time this is N substrate, so here we have N type and here we have what? P type, right? So it is P, N, P transistor formation will take place. Okay, so we are not intentionally forming this PNP transistor. Okay, so because of these substrate and the P plus and P plus, the source and drain terminal and the P-well process or P-well, because of that there will be a formation of transistors and the diodes will be there. Okay, so those transistors or diodes is called as what? Parasitic elements. Okay, so here one parasitic element, that is T1, transistor T1, that is an PNP transistor is formed. Okay, so this is one thing. Next what we have here, so I am explaining here, this is N substrate. Generally a PNP transistor means it will be like this, right? So it is a PNP. So P type material, N type material, and again P type material. So it will form a PNP transistor, bipolar junction transistor. So in this condition also the same will be here. We have this one is the P and this is totally the substrate N, and this P-well is nothing but again it is a P. So PNP transistor will form, and the transistor I am taking as T1. Okay, so here the transistor that is formed between P plus and N substrate and the P well. Okay, so here P plus, here I will write P between P plus of NMOS, of PMOS transistor, of PMOS and N substrate, and another one is P well. Okay, so these three will form what? The PNP transistor here. PNP transistor. That is T1. Okay, so these three will form the T1 transistor, that is PNP transistor. Now what I have here, another transistor I have here. Okay, so how it will form, right? So if you observe this one, here it is P, here it is P, right? Again here we have what, this one is N, this one is N. Okay, so actually here it will be formed with this N plus, so it is N, it is P and N. The transistor T2 will be formed, the transistor T2 will form between N plus. Okay, so here it is actually it is formed due to this one, right? Okay, so this is N plus. So similarly in this PMOS transistor, how the source and drain will be there. So similarly in this one NMOS transistor, we have the source and drain are of N plus regions. Okay, so here the transistor will form due to this, between this N plus and the P well and again N substrate. So it is NPN transistor. It is NPN transistor. Okay, so here we have NPN transistor. I am taking that emitter terminal as like this. Okay, so here the transistor T2 or the parasitic transistor T2 will form between the N plus of NMOS transistor. So here CMOS consists of one PMOS and one NMOS. Okay, so because of PMOS, so this is the parasitic element that is formed, transistor T1. And similarly because of N plus of NMOS and P well and N substrate. Okay, these three will form the transistor T2. Okay, so therefore here T1 comma T2 are the parasitic elements. Formed in P well. Okay, formed in P well structure. Then what happened here? Okay, when it is formed, what happened here? So that is nothing but, and again we have here T1 and T2 are the transistors. So here the substrate will consist of some resistance. Okay, so substrate will consist of some resistance. So here RS is substrate resistance. And again another resistance is there, that is RP. RP is P well resistance. So here combinedly, if you observe this one, here two transistors are formed, that is T1 and T2. So these two are called as what? These two are called as the parasitic transistors. Okay, so what are the parasitic transistors means? Because of the fabrication process here, okay, we will place our required NMOS and PMOS. So because of those elements, okay, because of those materials, there will be a formation of extra devices, that is nothing but parasitic elements. Okay, so here because of this one and N substrate and P well, we have PNP transistor, one parasitic element, and another parasitic element is T2. And we have the RS and RP, the resistances of this N substrate, and here we have the P well. Okay, so in the reverse case, we can extend the discussion for latch-up effect in N well structure also. Okay, so here what we got is nothing but two transistors. So this structure, whatever I have, this structure, I am placing here individually. I am taking off that structure from the diagram and I am placing here. Okay, so I am removing, I am taking this parasitic element structure and at the same time with RS and RP, and I am drawing here. Okay, and now I am going to explain how these parasitic elements will form the low resistance part between VDD and VSS. Okay, we will see that, right? So how these parasitic elements will form means I have explained, I have written here, but how this causes the latch-up condition. Okay, how these parasitic elements will causes the latch-up condition, we will see now. Okay, so here I will consider this one, this diagram that is formed with the parasitic elements and the substrate resistance and P well resistance. Okay, so the first condition here, for the sufficient current in the substrate terminal. Okay, what? For sufficient current, if the sufficient current flows in substrate. So I am taking that there is a sufficient current will flows in the substrate. If that sufficient current is flows in the substrate, so what happen? Okay, so we know that V is equal to IR. What is V? V is equal to I into R. Okay, so here if there is a current flow through the substrate and it has the resistance, okay, it has the RS resistance or substrate resistance. Okay, so suppose it is a resistance, through this a current is flowing means compulsory there will be a voltage drop. Okay, so here there will be a voltage drop. If the sufficient current is flows in the substrate, so there will be a voltage drop in substrate resistance. Okay, so here we have this RS is the substrate resistance. When there is a current of substrate current IS is flowing, okay, so what happened here? Here there will be a formation of our voltage drop will be there, that is IS into RS. Okay, so here Vs is equal to IS into RS. Okay, so this Vs is connected with the voltage drop across this resistor is connected with the transistor T1 base. This one is emitter and this one is the collector. Okay, so what is happening here? So if sufficient current is flowing through the substrate, and then there will be a voltage drop across the substrate resistance, and that voltage drop is connected with the base of the transistor. Okay, is connected to the base of the transistor T1. Okay, base of the transistor T1. Okay, so here Vs is connected to the transistor T1 base terminal. Okay, so Vs is connected to the transistor T1 base terminal, and it is enough to on the transistor T1, and it is enough to on the transistor. Okay, to on the transistor or to move the transistor into saturation. Okay, so here to on the transistor. So if this transistor T1 is on, okay, if the transistor T1 is on, the current will flows. Okay, so the IC current will flows here. Okay, if the transistor is on, more amount of current will be flows. When the switch is on, the more amount of current will flows. Similarly here, so this voltage drop across this substrate resistance is enough to on the transistor T1. So because of that, there will be a current flow will takes place. Okay, so that current flow will takes place, and that is flowing through the RP. RP is what? P-well resistance. Okay, so if a current is flowing, more current is flowing through a resistance, then voltage drop will be there because V is equal to IR. Okay, so this RP is connected to the base of the T2. Here base and emitter and collector, base of the T2. So this RP voltage drop is connected with the base of the T2, and that is also efficient to on the transistor T2. Therefore, both the transistors will be on. Therefore, there will be a less amount of resistance will be offered by the transistor T1 and T2, and the direct connection will formed between VDD and VSS. So this condition is called as what? Latch-up condition. Okay. So now up to this point, VS is connected to the transistor T1 base terminal, and it is enough to on the transistor. Okay, and it is enough to on the transistor T1. Okay. So what happened if T1 is on? Okay, so we will see here. If so, the next condition is if T1 is on, the current will flows through RP. Okay, so if this transistor is on, more amount of current will flows through the RP. Okay, so the current flows through the RP, and voltage drop Vp, that is equal to I into Rp, will obtain, and it is connected to the base of the transistor T2, and it is connected to the base of transistor T2, and it will on the transistor. It will on T2. Okay. So here what is happening? So after T1 on, the current will flows, and that current will drop will be there, obtained voltage drop will be there at the P-well resistance, and that is connected to the base of the transistor T2, and it is sufficient to on the transistor T2 also. Okay, so therefore the transistor T1 and T2 will be goes into the on condition. Okay, so here, so if the transistors T1 and T2 on, the transistors T1 and T2 on, okay, so they will offer less resistance between VDD and VSS. Okay, so this transistor is on and this transistor is on. Therefore, what happened here? They will offer less. When the transistor is in saturation, it will offer very less resistance. Okay, so it offers less. Transistor T1 and T2 will be offers less resistance, and because of that, there is a low resistance path, or here it offers low resistance path or less resistance between the VDD and VSS. So this condition is called as latch-up. This condition is called as latch-up. Called as latch-up. Okay. So like this, whatever the parasitic elements that are formed in this P-well structure, that is PNP transistor and NPN transistor, with the source substrate resistance and P-well resistance, there will be a formation of low resistance path between VDD and VSS, like this, what I have explained here. For a sufficient current, okay, more drop will be obtained at RS. Because of this voltage drop, the transistor T1 will be on. If the transistor T1 is on, means the current will flows, more current will flows, and that more current will flows through the RP, that is P-well resistance. Again here the voltage drop will be obtained. That voltage drop is connected to the base of the transistor T2. So because of that, the T2 transistor is also goes into the on condition. So both the transistors T1 and T2 on means it will offers very less resistance. Therefore the current directly flows from VDD to VSS with low resistance. Okay, so this condition is called as what? The latch-up. Okay, then how to avoid this latch-up? Okay, how to avoid this latch-up? So here we can avoid this latch-up. We can avoid this latch-up. The first condition is by reducing the RS. Remedies for latch-up in CMOS. Remedies means how we can, what are the methods to avoid this latch-up condition in CMOS. So the first condition is, the first condition here we have is, we can avoid the latch-up by reducing the substrate resistance. Substrate resistance, RS. So this is the first one. Okay, and second one is by reducing the P-well resistance. P-well resistance. And finally the third one is by using the guard rings. By using guard rings. By using the guard rings. Okay. So by using the first step, how you can reduce the substrate resistance. So we can reduce the substrate resistance by increasing the doping concentration of the substrate. Okay. So how you can reduce the substrate resistance? Generally we have the point that, so the resistance of a material, N-type or P-type material, will be reduced by increasing the doping concentration. Okay. So here my first point is RS we have to reduce the latch-up condition, or to avoid the latch-up condition I have to reduce the substrate resistance. How I can reduce the substrate resistance? The substrate resistance can be reduced by increasing the doping concentration. Okay. So doping concentration and resistance are inversely proportional. So here to avoid the latch-up I have to reduce the RS by increasing the doping concentration of the substrate. Okay. So that is the very important point, by increasing substrate doping. Okay. So this is one method to avoid the latch-up condition in CMOS. And the second one is how it will reduce. If I reduce the RS, how it will be reduced. So even though there is a sufficient current will flows through the substrate, but if this RS is less, okay, so if that RS is less, okay, if RS is less, what happened to the Vs? That is substrate voltage drop. Vs is equal to RS into Is, the substrate current, it will be decreased. Okay. So if Rs is reduced, Vs is equal to the voltage drop across substrate resistance, that is equal to Rs into Is. So that will be decreased. If it is decreasing means automatically that voltage drop Vs is not sufficient to on the transistor T1. Okay. So Vs is not sufficient to on T1. Okay. So if the transistor T1 is not on condition, not in on condition, so it cannot offer less resistance. Okay. So T1 cannot offer less resistance. Okay, T1 cannot offer the less resistance. This is very important point. Okay, so if Rs is less than decreased, Vs is decreases, and that Vs is not sufficient to on the transistor T1, so that there will be no latch-up condition will obtain, because it cannot offer the less resistance or low resistance. Okay, so the second case is what? By reducing the P-well resistance. Okay, so if you have Rs has the sufficient resistance and sufficient current, but we can also avoid this latch-up condition by decreasing the Rp. Okay, so even though this transistor is on, okay, if you decreases this Rp, there will be a less amount of resistance, less amount of voltage drop will be obtained. That is not sufficient to on the transistor T2. If this transistor is not connected, or it is in off condition, so there is no direct connection between VDD and VSS. Okay, this is another method we have. And the final one is by using God rings. Okay, how you can use that one means, here we will place an isolating material between this N substrate and these what we call this source and drain materials, that is P plus and N plus materials. So those are called as what? God rings. By using the God rings also we can avoid the latch-up condition. Okay, so this is about the latch-up condition that is obtained in CMOS circuits, and what are the remedies to avoid that latch-up condition. Okay, so here we have seen that what is the definition of latch-up, and after that I have considered a P-well structure. In that P-well structure, how the latch-up, how the parasitic elements will be formed. Okay, if that parasitic elements are formed, how it will causes the latch-up condition. Okay, so that is the explanation for the latch-up condition, how the latch-up condition will obtain. Okay, so this is the first point. After that we have second and third, right? Okay, so these three are the process that how this parasitic elements formed in this P-well will causes the latch-up condition in CMOS circuits. Okay, so if the latch-up condition is obtained means, okay, so there is no correct output we will get across the CMOS circuits. Okay, so and after that how you can avoid this latch-up condition means by reducing the resistances Rs and Rp, and at the same time by using the God rings in the CMOS circuits, so we can avoid this latch-up condition. Okay, so this is about the latch-up condition in CMOS circuit and its remedies. Okay, thank you for watching. Subscribe our channel.